do another one where I start the timer and start this mock assessment and then quit this mock assessment so that I can just get the hard solution. The hard problem to maximize my learning. There is a solution here which is good. So if I get stuck, I'll probably just look at it later. It does look like it's a harder one though. There are n children standing in a line. Each child is assigned a rating value given integer array ratings. You're giving candies to these children subject to requirements. Each child must have one candy, and children with a higher rating get more candies than their neighbors. Get more candies than their neighbors. Okay. So there's 20,000. I feel like I've done this one before. Isn't it just you initialize an array of all ones and then you, for example, 2, 3, 4, 5, 6, 5, 4, 3, 2, 1, and then you I don't remember the solution. So everyone gets at least one, and then if I'm bigger than my neighbor to the, let's say, right, then I just increment it the third child gets one candy because it's not higher than its neighbors. I see. So if you're bigger than at least one of your neighbors, then you get an extra candy. So, for example, here it's like I'm not bigger than 1, and then maybe 2 is bigger than 0, 3 is bigger than 2, this, and 5 is not bigger than 6. And you go all the way here, and here you go 2, so like 2 sweeps, 1 to the left, 1 to the right. And yeah, so 2 is bigger than 1, so it's 2, and then this is 3, and then this is 4. This stays as 1, and this can just be 2. And gets more candies than their neighbors. So suppose coming back this way, this was a 7. I guess it doesn't matter because in this sweep, in this left sweep, then I just say the max of whatever I have plus, if I'm bigger, right, then it's just this plus 1 or whatever I have is the maximum. Right, so conversely, if this was already bigger than this, then I can just keep this, right? Like, for example, this was like 8, but this is like 12. Then I could do 9 or I could do 12. But I guess if you do 12, it's because the other pass, so like going from left to right, you have to do 12. You know? And that was already the minimum. So you can't just say, well, if this was 8, why don't I try 9? Because if this was 12, this must mean this was 11. And then you would just break the thing. So I think the algorithm is just one pass like this, another pass like that, and then just, you know, I looks at I minus 1 for this pass to like the right sweep, for I in range 1 to the length of this ratings list. And if ratings of I is strictly greater than ratings of I minus 1, then candies equals 1 times the length of ratings, and then I wonder, I'm trying to learn the syntax, like can I do also like 1 for in range length ratings? Is this equivalent? I'll probably try that later on my own time. If this is bigger than that, then it must be yeah, so this is a minimum problem, but you're doing max, which is like kind of interesting because yeah. But you kind of need to do the max, because if you do 2 sweeps again, right, coming back from the other sweep, you might find something that's optimal for one side, but you still need to satisfy the constraint of children with a higher rating get more candies than their neighbors. So you can't just arbitrarily lower it. Yeah. So let's see. I sweep through all the ratings, and then if the ratings of I is greater than the neighbor on the left, then candies I is just gonna be candies I minus 1 plus equals 1. Or if the current candies at this particular location is already higher, it means that if I were to adhere to this right hand side value, I'm actually breaking some constraint on the other sweep. For I in range, so now we're just kind of going back. So in this case, we're starting from here. Minus 2, right? And then going all the way to 0. So now if ratings of I is greater than ratings of I plus 1, so the first iteration checks the second to last to this length of rating minus 1, which is the last one, so it checks out. So if it is bigger, then candies of I must be whatever I had, comma, candies of I plus 1 plus equals 1. And I guess what if a case where like this or something. I was worried like the last element could have like some very high candy value, but that's actually not possible because in order for that to happen, this last element must be, let's say, bigger than 6. Even if it's 6, um, this won't trigger. So like I was just afraid like kind of going back and I just artificially pump up this value, but that turns out not possible because in this case, this would just be a 1 and this has to be at least 2 or keep whatever its value is. So then return the sum of candies is my guess. Oops. Right, I'm not assigning anything. So keep the current value or look at the left neighbor's value and increment by 1, or look at the right and increment by 1. Oh yeah, I did solve it about like a month ago. All right. So that's sort of sad. So maybe we just go back, do another one. um, no, because you do so many and you're like, oh, actually, maybe I just do, yeah, let's, I mean, 32 minutes is enough time. So let's kill this and then let's see if there's a hard one. Um, yeah, this one is quite easy. This one is you just build a mask via yeah, for I into the power of length of nums, and then you just right shift the number by whatever iteration you're in. So for example, here you go from 0 to 7, and then you write, like, for every iteration you right shift your I by, you know, for j from 0 to 2, you would just right shift it, and then if it's odd, it means it's a 1. Basically, you're looping through the binary of 0 to 7, and then you're just kind of appending it to an array and printing it. Okay, let's just try to get another one. Pause this to find another one. Okay, well, I can't find another hard one, so maybe I just do this medium one, which oftentimes turns out to be harder than the hard one. So you're giving away books, thickness, and height. Shelf width. You want to place these books in order onto bookcase shelf that have total shelf width. 2, 3. Okay, 2, 3, 1, 1, 1, 1, 1, 1, 1, 2, 1, 1. We want to place these books in order into bookcase shelves. Okay, we choose some of the books to place on a shelf, such as the sum. So we always put it in order, but then the organization is up to us. Here, what if we did like this, and then this, and then, so we did this, the height is 3, and then we did 1, 2, 3, 4, 5, 6, 7. Interesting. 1, 3, 2, 4, 3, 2. So 1. It's width and height. Okay. Trying to come up with cases where greedy doesn't work. So suppose one had thickness 2. Doing 2 here would result in 3, 3 would result in 6, and then you can still fit 4, 5, 6, 7. Actually, hold on. Suppose thickness of 2. And then this 2 goes up here, and it's like 3, and then this, and then 4, 5, 6, 7. So I guess the hard part is like, for this, how do you know if 2 goes up here or down here? Like in this case, it does, so 1, 2, 3 is still 6. 4, 5, 6, 7. It's still the same height. 4, 5. Oh no, it's not the same height. We're high by 2. So what makes this 1, 2, 3 better than 1, 2, 3? One, two, three, 1, 2, 3. 1, 2, 3 so far is always gonna, I guess 1, 2, 3 will always result in a higher height. So maybe DP, like if I place 1 and then 2, then my height is 3, and then if, yeah, like a current width of 3 is less than shelf width, so that's always a good strategy, because you never will, like if you can already fit it in one shelf, you know, you're obviously always better off doing that. Now if you have 3, then you can say, do I want this 2 to be here, and then 3 to be here, or do I want 2 to be here and 3 to be here? But then like 4 or 5 stuff, like on each shelf, so like let's say, you know, we only had 1, 1, then obviously it's 1, and then we have 1, 1, and 2, 3, then the answer is 1 plus 2, which is, or sorry, the max of this plus the current shelf, which is 0, so that's 3, and then so the answer is 4, right? But I'm wondering if this 4 is derived from, let's say this was problem 1. This is the second problem. Is this some function of solution of this, you know? each shelf, on each shelf, suppose there's no 1, 2, 3 and we're just looking at this. On each shelf, it doesn't really ever do us any good to start a new shelf if the thing isn't exceeding the length or the width of the shelf. So for example, if 6 had width 2 is when we consider either putting in this shelf or the next shelf. But in this case, everything is width 1, so we're always good to do this. So every single shelf, if we can be greedy and fit it in, that'll minimize height, because obviously if you start a new shelf, that's not that good. Kind of reiterating the previous point, but then now my next step of my thinking is, suppose now 1, 2, and I insert a 3. The 3 exceeds it, so I'm wondering if the 3 exceeds it, if it's sufficient to say, well, the decision is I either have put the second to last and the last one down, or are there some cases where 3 is so wide, like 3 or something? Like if three was with 3, I don't even have to make the decision of putting 2 down, because then 3 can't actually fit. So I'm kind of, the constraints of the problem forces the 1, 2, 3 situation. But if 2 was, like, let's say 2 had width 1, and then 1, 2, and then this block of 3. Would I ever make the case that I'd have to consider more than one block in the past to move down one shelf? So suppose the width was like 1,000, right? And then, this was like block 50, and block 50 is like quite wide. Do I only consider block 50 and block 49 as candidates to move down, or do I consider things before? Since we have to put things in order, I don't think we have to consider the things before. In fact, do we need to consider 2 if it was a height of 2? Yes. I guess if 3 had maximum height, then we need to consider if 2 is the minimum height, then we don't want to put it down. If 3 is the this is way harder than the previous hard problem, so I see. I see. So for this shelf, I add height given like there's a bunch of heights, right? And then the height I'll add is the maximum that I fit in this shelf minus the minimum I fit in the shelf. So if I need to start a new shelf, then I need to consider how much of that height I can hide. So if I need to start a new shelf with the height of like at least 3, then I should consider hiding the height here. Like, because I have to add 3 anyway, that's a sunk cost. So I need to look back to see because 2 and 1 adds an extra height of 2, and if I have 3, it's a sunk cost, so I need at least, another 3. But if I look backwards, let's say 2 was a height of 4. Um, if 2 was a height of 4, then we can put it. If 2 is not a height of 1, then it's always worth pulling it down. Suppose 2 was a height of 4, then this will be 4. Plus 1 is 5. But what's the mathematical relation? That's what I don't understand at all. Because obviously if you pull as much as you can to the next shelf, and this 3 is a sunk cost, and you have like a bunch of like 2s and stuff, and then you have a super long thing, then and you go to the second shelf, then you kind of minimize the height of this shelf while hiding a lot of the height underneath this 3. But then the thing is, you don't really know how long the array is, so then like the more things you add in the second shelf, the sooner you might have to start the third shelf. Which is kind of the trade-off. So, and then there's 1,000 of these, so I guess can this be a search problem where we start with 1 and then 1, 2? And then for every new block, we consider putting it on the same shelf or the next shelf. And then, so same shelf. So for example, place block 1 and then do some calculation, place block 2 on same shelf or next shelf. So in this case, it considered both possibilities, and then on the third one, we say, we have to place on the next shelf. So we do 1, 2, 3, or 1, 2, 3, or 1, 2, 3. I guess when can we start pruning stuff? Because if it's like a binary tree, it's like 2 to 1000 obviously, so that's quite big. So if I say 1, 2, 2, so 1 is my root, and then 1, 2 in the same row, or 1, 2, and then here it must be 1, 2, 3. And here it's 1, 2, 3, or 1, 2, 3. I'm wondering if I could prune some of these. So obviously, if I fit it in the same, if the number of shelves, which is 2, is less than this number of shelves, and I have a lower height, then that's, I can eliminate this, right? Lower shelves, lower height. One, 2/3 versus 1, 2, 3. I can also eliminate this. because I can eliminate this if, or can I? Yeah, I can eliminate this because I have the same number of shelves, but this has a smaller height. Or can I? Because we don't know what will happen with like 4, 5, 6, 7. So you could do 4 here, but you have to do 4 here, right? So maybe not. So here, then I end up with which is a height of, whatever. This is a height of 1, 4, 5. And this has a height of 3 plus 6. So this has a higher height, but then I guess shelves don't matter, right? It's the height. You also have like another thing, which is like thickness taken. So 1, 2 takes up 4, and then 3, 4 takes up 3. So it's like the first whole shelf plus this, and then this is no, probably more accurate to say the index on the current shelf. So 3, 4 would give us like 1, 2, 3, 4. So the index, it's like 0 base, 0 and 2, and then here it's 1, 2, 3, 4, and then this is index 0. So I actually have more shelf space here, and it's a lower height. So I can prune this. What about 1, 2, 3? 1, 2, 3 gives a height of 6, and 1, 2, 3 is at 1. This one says 1, 2, 3 has a height of 4, but its index is already at the end. One, 2, 3 says it's 7 and it's 0. Suppose this 4 had some width and it's of height 7. Then it can just remain 7 here, but here it has a height of 4 and let's say width 2, 7, then actually this will need to go like 4 plus 7. And it needs to go to the next so let's say the fourth one instead of this is 2 by 7 tall. So then here it would be 11 and the width would be 2 if we had to add that. it'd be 3, but it'd still be 7. That's quite weird. 1, 2, 3, and then 4. Here's like 1, 2, 3, 4. 1, 4, which is huge. Right, so I guess my point is I can prune this one because my height and I have less height and less shelf space, and so I can prune this one in this layer. But in this layer, I couldn't prune this one. But let's keep going, because then this one here would say one, 2, 3, 4, which would be 7, and then 1, or it could be 1, 2, 3, 4, which would be 8 and 0. So this 5, 0 can kill this. It can also kill this. And it can also kill this, actually. So height is this. Anyway, I'll probably implement this a bit later because I don't feel like doing it now, and I have other things to do. But then just note to self, this is gonna be and the first thing would be like total height. Like you could just like do books.pop 0, and that'll be your like first index, and Or yeah, I guess I might just do it now. Whatever. Okay. This is width by height, so width is 0 and height So I'll just add a height here. So like this. Meaning if this equals shelf width, then we need to we can't consider this, we must consider that. Which is the width. So suppose, so this says I start at 1, so that I can only have a width of 3. So let's say this was 2, then I actually start at 2, and then so I could support a width of 2. Meaning this is, if this was 2 and next node was 2, it equals 4. So it would only fit, not fit, if it was strictly greater than 4. So this is actually less than or equal to shelf width. Then so 1, 2 will have 3. This is 3 and this is 3. This 3 is derived by the maximum of the existing this is just the maximum of whatever the next node is, comma, cur node of 1. Right, so if this was some height, then this is some height. Like if this was 3 instead and this was 1, then we would actually take the 3 of this one, so the current node. Otherwise, we would take the next node's height as the representative height of this current shelf. So this adds stuff to the same shelf. And here we can always add to the next shelf. So if we add to the next shelf, then this next node the width will always start here on the width, and then the height will always be just whatever the current node is plus the next node's height. So now we can generate this, but then this gets out of hand quick because of the 1,000, so we need to handle the pruning situation. So instead of Q append, I'll just do next Q, which is our fringe layer. And then here we'll say that. The reason why I wanted to decouple this is because I want to pop everything from Q and then examine the next book to add, and then for however the cardinality is in the current layer, I just want to be able to add maximum 2 children, so like a 2 to a 4, like a binary tree situation for your next layer maximum. And then in the next layer, once the next layer is generated, I can prune it, and then once it's pruned, I'll do this update. When everything's when we're at this layer, there should be no more. It'll be the last iteration of I. So suppose there's just 2 books, then 1 to 2 just says hit 1 iteration, Q just adds these 2, and then next Q would be this, but it will get reassigned to this. And then so after we exit this loop, we just go ahead and examine the minimum height. For now, to prevent explosion, we need to do like for some pairwise comparison in each node. So how do I prune? Yeah. Actually, our tuple references, probably not. just do a pairized comparison, and then so if next q of I of 0 is less than or equal to next q of j of 0 and next q of j of, so this is saying that the height is less, and next q of I of 1, and then this is saying that how much shelf space you have. So we go backwards. So pops don't interfere with this loop. So we go backwards, and for example, the last element is none. Then we go ahead and pop it. Mark for popping. So in this case, let's say we end it here, then this Q is this, and then current node will be this, and then next node will be the second node. And then if the widths fit, then I go ahead and want to do this on the same row, which is just the tuple where the height, the width is going to be, the width is just going to be the sum of these two, which is the same as this, and then the height is just going to be the maximum of this inherited height, or whatever node we're inserting. And we can always add to next shelf, so there's no constraints check, and we append basically however wide the next node is, because that's, you're starting a new shelf, so then the width is always that. And then the height, of course, will just be the accumulated height plus the height of the next node. And so if we were to, let's say, ignore this, then q equals next q, we would inherit this. And if we added 3, then we would just keep popping this, and then per each of these and these, I would just add children. And then once we add children, then we would say, well, this next queue actually is, whatever the next layer is. And then so for u in range of this, and then for v in range of +1, so your pairwise comparison, then you're just going to make sure that the width and height are not going to be strictly suboptimal for index v, else v is marked as none or marked as pop, something you pop, and then we just reverse iterate through next queue and then pop everything to minimize the children explosion. And then once this is all said and done, so let's say, this is this, we have iteration of 1. Next queue would just be this, so that means queue would have the last layer at the terminal index. If we have that as a terminal index, then we simply just go through yeah, there's probably like a shorthand for it, but I don't know what it is. So for element in queue, min of because even if you add 1,000 of 1,000, that's 1e6. Anyway, minimum of smallest height, comma, element of its height, which is going to be 1. The diagram and this seems to be off. So this one, we're saying 0 is the width, and this is width, and this is height, and this is the width, and this is the height, and this is agnostic. And then here we're saying, okay, final thing, so just go ahead and look for the smallest height and return that. This is actually not super duper easy. So I only have one while loop, and I always pop this, so I should always be able to exit because of this. I don't really add anything to queue until here, which means I'm going to go to the next iteration. Print queue. Print I comma q, actually. So I pop 3, and two comma 4, and mm-hmm, mm-hmm. So that looks okay. Next cube is of this length, and oh, I see. Because when I overwrite, okay, I see. If next u q of u is not none, and next q of v is not none, and at least the values are expected and matching. One 5 is 1 5. That's good. Why, I guess, why doesn't 2 5 exist here? Keep in mind I of 4 means 5 because I of 1 is this. So I of 4 is this. um 3, 3, and 2, 4. And then I see 4 is actually 1, 5. And then, okay, 2, 5 is here. 2, 5. And 3, 5 is here. Next, this and so these 3 got pruned for some reason. But 1, 8 didn't get pruned for some reason. I don't get it. Where's the bug here? You in range this. Oh, it's I. Okay, it's U plus 1. Yeah, that would corrupt the whole thing. Two 5 is, yeah, 3, 5 is okay. And then 1, 6, and then This is the last layer generated on 7, which is 1, 2. And so 3, 5 is what we want actually. And so 4, 6, yeah. For 5 is where we don't get 4, 6. So probably the height update is wrong. So add to this. Oh. I need the max for this level. So let's do this. Max for this particular level is max height for this particular level is this, and then So the current node inherits the max height for this particular level, and if this exceeds that, then we want to update that. But then what's the total height? Total height is normally just the parents, unless this is bigger than this. In this case, I add the difference. So I add 0, where I say, well, this height is bigger than the current layer's max height by, let's say, 1. Then I add 1. And then this part says that, because if I start a new row, its height is just going to be this guy's height. And then this still checks the first two, because I don't really care about current row height, I care about total height. And this is still checking the total height. And if I get rid of the print, will I get a correct answer here still? So let's try to submit. Okay, well, I give up. Fucking DP. Okay, so they do a DP of length n plus 1, and then what? I really hate DP problems, to be honest. While j is greater than equal to 0 and max with minus books. Okay. So for any given book I look backwards for all the books before, and as long as the width is greater than or equal to 0, then we subtract that, and then the max height is the max of the max height, comma, books of J1. So I guess the max height of our current row right? And then, so the max out of the current row, and then so dp of I, i.e. our current book, equals the minimum of dp of I, comma, dp of j plus current row's max height. If I'm at book I, why do we exclude book I's height from max height? dp of I, meaning, oh, dp of I is book I minus 1, which is book J. So I see. That's why. Because I here is really book J. Well, I minus 1. So maximum J value is our I, book I. So the minimum of the current book we're looking at, comma, some book prior plus max height. I don't. Max height of our current row. Yeah, no one really explains anything, which is extremely annoying. What the fuck is a knapsack? So for each book I look back J number of books where I can fit it all into one shelf, and the max height is this maximum height of my look back. So not the maximum height of a current row, but it's just the maximum height of, if I look back J books, then if I look back J books where J books is something I can shove in a row or partially shove in a row, then what is the maximum height of this look back? So with that, DP of this book is just going to be some look back index J plus the height of the max height. So I guess this is trying to say if I look back J books, I can at maximum get, this many books to the next shelf. And then for each of those possibilities, but why max height? I don't get this max height. It's a running counter that corresponds to J. So DP of I has some height, and if I look back J, DP of J has some height plus max height. So I guess this is saying I want to place it on a new shelf, and this is saying I don't want to place it on a new shelf. So this is, okay, so this is basically saying for every book I look back and say, I have J books possible, and in each of these intervals, I can, like for example, let's say you can fit 5 books and J can go from 0 to 4, and then you can basically chop and say, I want to put 1 book, 2 book, 3 book, 4 book, 5 books to the next shelf. And this is what that represents, and then this represents not putting any of those books on the next shelf. And I guess then if you break this, then you have to put a book on the next shelf, so you would do that update here when you go to the next iteration, because then your I would increase to the next book, but then your look behind would say your maximum height is going to be this, which will have your this would be infinite on the new layer, and then DP of J will have basically the previous height plus the height of your book if you have to add a new layer. So then each iteration is a new book, but also perhaps a new layer. This is actually extraordinarily complicated compared to the first quote-unquote hard problem.